Good morning, ladies and gentlemen. We're from LaSalle College, and our team number is 60667. The topic of our research is lifted up. The word lift here is actually another word for elevator. So you can probably guess that the topic of our research mainly focuses on comparing different lift systems. So before I begin my presentation, let me first ask you a question. Did you ride in any lift today? I suppose you have, since this is the 28th floor of this building. And unless you walked it up the stairs, otherwise you must have been in a lift. So, do you remember how long you waited for the lift? 30 seconds? 1 minute? Or 2 minutes? I suppose everyone would get pretty annoyed if one of these situations occurred to you. You're in a big hurry, and then you have to wait for a lift, but you just don't know why. The lift just wouldn't come down, and you have to wait for so long. So, and this is what motivated us to do this project. We try to use maths to solve this problem. We try to answer the question, how can we use the most efficient lift system to reduce our waiting time and traveling time? And so, let us now come to the areas of our study. Firstly, we focus on mainly commercial buildings. And secondly, we focus on three lift systems, three different kinds of lift systems. The first one, lifts that serve on all floors. The second one, lifts that stop on even or odd floors. And the third one, lifts that stop on the upper and lower floors. Now, we come to the directions of a study. Firstly, we have set three values for simplicity for the number of floors, and they are 20, 40, or 60. We chose this so as that the 20 will represent the relatively shorter buildings, 40 will represent the medium height ones, and the 60 will represent the relatively taller ones. And we have also set the interfloor height to be either 3.75 meters or 4.5 meters. The interfloor height is the distance between two adjacent floors. And the third is the rated car capacity. We have set it to be either 15 persons or 21 persons. And the rated car capacity is the maximum number of passengers a lift can hold. Also, we have assumed that the population is uniform. That means in a building, a same portion of population will go to the same on every floor. And also, the last one of our assumption is that we're considering only the up-peak traffic. That means we consider all the cases when the passengers travel up the building and also during the peak time. Now, we come to our next point, and it is the criteria for our comparisons. We're considering 4 times for our comparisons. The first one is the round trip time, which is the time the lift takes to go from the terminal and to the average highest reversal floor. We'll explain that later, and back to the terminal. The second time is the average journey time, which includes the average traveling time and the average waiting time. The average waiting time is the time from which the passenger first registers a call for the lift, and then until he enters the lift. The average traveling time is the time from which he enters the lift and he leaves the lift to the time he leaves the lift at his desired floor. And the average journey time is adding these 2 times together. And so that is when he registers the call to the time in which he leaves the lift. We have also considered other things too, and we must focus on our goal now. And what is our goal? I think all of you can guess that it is to minimize all the time here. Mainly the average journey time and the round trip time. So, let us find out what are the factors that affect the performance of the lifts. The first one is the average number of stops. That means the average number of stops that a lift makes when it journeys up. And the second one is the average highest reversal floor, which we have mentioned earlier. And that is the average highest floor that the last passenger alights. So let us take an example. For example, 4 passengers. 2 passengers who wants to leave at the 2nd floor. 1 passenger wants to leave at the 7th floor, and the other one, the 19th floor. Then the S here will be free. the second floor, 7th floor, and the 19th floor. And the H here will be the 19th floor, as that is the highest floor that the passenger will go to. So, after considering the S and H, what else do we have to consider for our calculations? And that will be the passenger arrival rate. We have chosen two models for the passenger arrival rate. One is the uniform distribution, in which at any time, the arrival rate is a constant. The second distribution is the Poisson distribution, which looks like this. And it is determined by the Poisson distribution function curve. Now, let us go to our calculation details. For the formulae for uniform distribution, here is the formulae. And for formulae for the Poisson distribution, the formula is like this. It's a little bit different from the two distributions have different formulae. And we assume that the Poisson distribution is more accurate, as in real life situations, there will be differences in the arrival rates during the peak time, and it will not be a constant. Now we come to the next highlights of the calculations, which is how to calculate the different times we have mentioned earlier. For the round trip time and the average traveling time, it mainly depends on the highest number of average number of stops and the average highest reversal floors. And for the average waiting time, it mainly depends on the round trip time, because these three variables here are actually constant, we have assumed it to be. And the average journey time is a summation of the average waiting time and average traveling time. So actually these equations are mainly for calculating times for the all-floor system. So you may ask, what about the other systems? How about the even and odd systems? So to calculate the times for this kind of system, we have modified the formula, because the distribution of passengers leaving at various floors is different. And so this is the equation that we modified, one for the even and one for the odd. As for the last system, the upper and lower floor system, time is saved by a jump from the terminal to the mid-levels when passengers want to go to the upper floors. So we have to include that jump, that express jump, when we calculate the time too. So this is our equation when we calculate the times for this system. So now we come to the results after our investigation. The inner floor distance, whether it's 3.75 meters or 4.5 meters, it seems that the results are more or less the same. And we'll mainly focus on the round trip time and the average journey time. For uniform and Poisson distribution, it is found that the results are similar. When the number of floors is 20 or 40, the system that goes to the even or odd floors is the most efficient. The second one is the upper or lower floors. And quite surprisingly, the lift system that serves all floors is the least efficient. However, when the N is increased to 60 floors, the upper lower system is the best, and the even odd system becomes the second best, and still the average, the all floor system is the worst. So let us come to the conclusion of our project. Although the all floor system may seem quite convenient, as because no matter which floor you want to go to, you can enter every one of the lifts. You don't have to mind which lift I have to go to. But according to our study cases, it is inferior in general when compared to the two other systems. As now we'll consider the number of floors. When it is 20 or 40, the best system is even or odd floors. And when it is 60, the upper and lower floors is the best. Our presentation may come to an end now, but the research on the efficiency of this system will not come to an end. I hope that after listening to our presentation, you can carry forward the research on this topic and to think about other cases and other combinations of lift systems. So the next time you ride in a lift, I hope that you can remember our presentation and think more about lift systems. Thank you.